So that was the last thing we've got to in the last video. We were trying to get the value of k, the constant, to clear up the units in the phase of the mechanical wave function. Okay, so now the mechanical wave function will take the following form: psi equal a, like we've agreed. We're not gonna write x and y and z to save some time in space. Sine k sine s, the phase, the constant action, over h bar, right? And now the units is clear because this one right here had the units of joule times second, and this one right here is the action function, so it means it will have this the same exact units, that is joule times seconds. So the units will clear this from the denominator and the numerator, and the argument will be unitless, like we wanted from the very beginning. Now what do you think we're gonna do now? Now we've got the wave, the possible candidate for the wave equation. To get the equation, all what we need to do is just like to plug in the normal wave equation. The normal wave equation said that the Laplacian of the function psi will equal to multiplied by the square, the speed of light squared will equal to the second partial derivative of this function psi. That's cool, but actually this is not c. Sorry, in general case that one is not c, but it is u, right? That's the phase speed. That's the phase speed. So what we're gonna do about that? How can we get the phase speed? To get the phase speed, we're gonna get back to our plotting here, which is like, you know, we've assumed the phase to be constant phase, to be the constant action, and it's moving, that at time t, and that one at time plus dt, and that one here is ds, right? The distance, this surface, level surface has moved, and now what we want to get the speed of this phase, the phase speed, u. So to get the u actually is nothing more than ds dt. But how can we get this ds right here? Actually, we're gonna start from the simplest argument. We know that s is equal to w minus et, right? And at the same time, we know that this s right here is constant, it's not changing, so that means when you take the differential of s, that's equal to dw minus et, right? Actually, like we said, we know that this ds right here is equal to 0, so that's all equal to 0. So dw equal e dt. But actually, the value of dw is nothing more than the multiplication of the gradient, the norm of the gradient of this function, times the s. Can you remember the value of this one here? This value, we have derived this value in the above, in the last videos, and we knew that it will equal to e minus v ds, right? That's really good. That's really good. So far, so good. We need another page. So dw is gonna equal e dt, but dw equals the gradient of w ds. Therefore, the gradient of w ds is equal e dt. Therefore, ds dt, what we need, which is u, is going to equal e over, which is going to equal which means u is going to equal e over the square root of 2 e minus v. So far so good. We're going to continue in the next video. Thanks for watching.